The last presentation of today is actually on the package grounding effects on electrical test performance in contactors. And the presenter is Jeff Sherry from Johnstech International. And so Jeff Sherry is the principal engineer and on the RF, HSD, and R&D engineer at Johnstech International in Minneapolis, Minnesota. He holds 25 engineering patents and several more pending. Jeff has been an integral member of the Johnstech team for over 20 years. He holds a master's in electrical engineering from the University of Minnesota and has been working in MMW applications for over 35 years. So the millimeter wave applications, basically. So with that, I want to also thank all of you for joining this presentation. And I do want to mention that Jeff has had an emergency in his family. All prayers for him. But thanks to Jeff for sending out his video of the presentation. So we'll go over the presentation.
This is Jeff Sherry from Johnstech International, and today I'm going to present a paper on ground inductance modeling of TestContact. I'm going to talk about today in the agenda why ground inductance is important, the devices that are susceptible to ground inductance in a test system, how to simulate ground inductance in a contactor. We'll go through a back of the envelope ground inductance calculation, which will get you pretty close to what the actual ground inductance of the contactor is, or the system. We'll do a comparison then of a signal ground signal and a ground signal ground in a passive coupler. We've modeled up two different couplers, one with signal ground signal, one with a ground signal ground. And I'll show you the difference in performance and TDR response by having the extra ground around the signal versus just one ground around the signal. We'll go through examples of ground inductance. I've got one on a filter and an amplifier that will affect performance. And then at the end, I'll show methods of improving grounding for the device, the contactor, and the board. All of them play a real big part in being able to test, especially devices that are very sensitive to ground. And then we'll conclude. The devices that are susceptible to ground inductance in the test system are power amps, high gain amplifiers, usually above 20 dB, filters such as surface acoustic wave and bulk acoustic wave filters. And a SAW filter basically is widely used in mobile devices or automotive applications to filter both the RF and the IF frequencies. A SAW filter uses the piezoelectric effect to turn the input signals into vibrations that are turned into electrical signals at the desired frequency range. A BAW filter, on the other hand, the acoustic wave propagates on metal patches on the top and bottom side of the quartz to excite the acoustic waves, which bounce from the top and bottom surfaces to form a standing acoustic wave. The frequency at which resonance occurs is determined by the thickness of the slab and the mass of the electrodes. Other stuff that's very sensitive to grounding is high-speed digital designs, typically above 10 gigabits per second. Other high-gain devices, such as maybe receivers that have they have to boost up input receiver signal to get things to work. Also, voltage-sensitive devices, such as high bit count DDAs and A to Ds, where if the part is operating at a voltage, if you divide that by 2 to the number of bits, that gets you the voltage per bit. And if that's really small, ground inductance could play a big part in making sure that you have all the significant bits. This slide basically shows the capacitances and inductances in test system. On the right-hand side is basically the equation to calculate the inductance of a microstrip line on a circuit board, based on the width of the trace, the length of the trace, the thickness of the trace, and the height above the ground plane in the substrate. On the left side is basically a picture of a contactor that kind of shows all the elements where the inductances and capacitances are. If you look at a path, the inductance you'll have on the low board, then you'll have a series inductance of the contact, and then an inductance of the pad. And the capacitances basically are anything that goes from them metal surfaces to other metal surfaces. For instance, the formula on the top left is the capacitance between two contacts basically, and it's the dielectric constant of the housing material times the free space constant or permittivity, which is 8.854 10 to 10 to the minus 12 farads per meter. And then the area of the two surfaces divided by the distance that they're apart. And that gets you a really good calculation of the capacitances between pins. In this slide is basically what we're going to be doing in the back of the envelope's calculation is we're going to be converting the most likely rectangular area of the ground insert for a QFN package. We're going to convert it into a effective diameter and then use that diameter in a self-inductance calculator. That this one I just basically pulled off of Google, or I Googled wire self-inductance calculator, and there's multiple sources that give you pretty much the same answer. But from there, we'll convert the rectangular area into a equivalent diameter for wire, and we'll put that in the equation. And on the right side, I've actually did that for different wire diameters, and you can see from the columns that obviously the shorter the length, the lower the ground inductance, or the lower the inductance of the wire. And as that wire diameter gets bigger, the inductance goes down, and it's not proportional. So you can't double the wire diameter and get the inductance to basically decrease by half. It decreases by less than half usually. This is important when you're thinking about ground inductance systems and you have maybe a thick contact. It'll have less inductance, but it won't be a factor as much as maybe having two thinner contacts hitting the same ground inductance path, basically. This is a calculation of the back of the envelope ground calculation. Basically, it's very similar to resistances in parallel. You have the inductance of the insert times the inductance of the contacts divided by the sum of the inductance of the insert and the inductance of the contacts. Where the inductance of the contacts is basically the inductance of one contact divided by the number of contacts in parallel. Where the inductance of the contact is the self-inductance plus the mutual inductance, where if the contact is in a ground insert, the metal insert basically is at zero potential, so the mutuals are basically zero in this case. So in a metal housing, the mutuals basically are zero, and so all you're left with is the self-inductance. And you get that from contact testing. The insert inductance is basically found using the online calculator shown in the previous slide. And there I just searched wire inductance, where the wire diameter is the converted insert area from the device interface to the board into an equivalent wire diameter, basically. And the wire length is basically the height of the insert. Here's a picture of that insert, and the values for the contact inductance and the mutual inductance are basically pulled from a third-party test report. The number of contacts in this insert is actually 12. The height of this insert is 0.763 millimeters. So if you go through the math, you can see that the inductance of the contacts is 0.0194 nanohenries. Now, if you take the surface area of the insert itself, and then you figure out using the equation pi r squared equals that area, and r squared is basically d squared over 4. And from there you get a wire diameter of 8.322 millimeters. And using the wire inductance calculation, you can find that the insert inductance is 0.0521 nanohenries. And if you go through the math from the previous slide, you can see that the total ground inductance is basically 0.014 nanohenries for this particular insert. This slide shows basically the capacitive structures of a 5x5 copper insert, where the capacitance is basically the device pads to the low board pads. You've got some capacitance from the insert to the peripheral contacts. You've got some capacitance from the insert contacts to the ground pad, and you've got some capacitance from the device pads to the insert pad. Again, between two plates, the capacitance is the dielectric constant of the material between the two plates times the constant times the area divided by the distance between surfaces. Once you've got that inductance, what you can do, in this case I used ADS, you can basically model the test contactor showing the ground inductance effects. And here for most devices, they have an input and output. So they have a termination on the left-hand side going through a contact pin, where terminal 1 is basically the board side connection, and terminal 5 is basically the device connection. And then you have the DUT, and then you have another contact for the output. There from the DUT, you go into the connection that would be at the device side and come out of that to a termination on the board side. And that inductance basically is the ground inductance that you would calculate from that insert. If you wanted to know what the equivalent circuit of the pin is, this is basically the equivalent circuit. This matches really well with the measured result, but in all cases, it's probably better to use the measured result because the equivalent circuit is always just an approximation of the measured results. But the nice thing about this is if you look on the left-hand side, you see the impedances of the terminations. It's basically a ground signal ground configuration because the top and bottom terminal are basically set to 0.001 ohms, and that represents ground. In ADS, you don't want to set it to 0 because it'll blow up. On the right side is basically the device terminations. Again, they're the exact same as the low board side. The only difference is everything is symmetrical in this case, except for we've added a contact resistance. Typically, the contact resistance is more important at the device side because you're dealing with, in some cases, matte tin, and the contact resistance between a gold surface and matte tin is a lot higher than maybe the low board side where you've got a gold-plated pin or some other material with a gold-plated trace, and so the contact resistance there is minimal compared to the device contact resistance. So we've added that basically to generate more of a FET model for FET devices, because in that application, the RF signal out is basically also the same path as the DC voltage in or current in. Now we'll get into the measured data, or model data, I should say, from a ground signal ground 20 dB coupler with and without contacting. So the red line is basically what the device is, soldered to board. And then the blue line is basically the device in the contactor. Now you can see that there's a delta difference of a little over 1/10 of a dB, and this is basically the insertion loss of the contactor. Anytime you put a device in a contactor, you're going to actually degrade the performance of the device a tad. How much it's degraded really depends on the contact or the low board inductance, the size of the contactor, the length of the contacting device, whether it be a spring pin or in our case, a roll contact. But the nice thing about this is the roll contact is basically a solid contact. So you can see that the delta difference is very consistent over the bandwidth of the coupler. And because it's a solid contact, you're never going to have any variation. It's always going to be the same, whether you test first chip or the 10,000th chip or the millionth chip. This shows basically the same ground signal ground 20 dB coupler, and looking at the return loss between the device and then the device and the contactor, it's very similar. There's not much change, and that's because in this frequency range, the return loss is actually very good compared to the device. So you're going to see minimal change in the return loss of the device when you're testing it. And that's one of the key takeaways from this slide. As long as your contacting system is quite a bit better than what you're actually measuring, then you're going to actually get results close to what the device performance actually is. This will also eliminate a lot of false failures too. Here's the same coupler in a ground signal ground mode, and it shows basically the isolation, which is the it's not the through path, it's not the coupled path, but it's basically the isolation path. And you can see here, because the contactor itself has such much better isolation, in fact, about 20 dB or more isolation, which is 100 times better. You can see that basically the device isolation and the device in the contactor is identical, and that's because you have so much margin. Now this is actually that same, or a different coupler, I should say, in a signal ground signal configuration with the same contact, and you can see this slide shows the characteristic impedance, or a TDR plot. And you can see that the impedance is actually well matched, as to be expected, because the return loss was so good in this band. You can see it's basically 50 ohms plus or minus a tenth of an ohm in this case. Now, if you take that same configuration with the same pad sizes modeled up in a ground signal ground, because the grounds there's two grounds close to the signal, you would expect the TDR plot to decrease a little bit. And sure enough, from this plot, you can see that both traces, the impedance is a little bit less than 50 ohms. It's still really good. It's less than basically 0.15 ohms from 50 ohms, so it's actually really close to 50 ohms. And so the return loss still would be very good. Moving on, if you take an ADS model, the device may be soldered to board, and I've got a picture on the left here. And the equivalent circuit of that would basically be an S2P file of the RF path for a ground signal ground. And you can see it's terminated. In this case, ADS for this device, I'm just using a 1 to 10 gigahertz sweep. And if you look at the bottom side, if the device is in the contactor, you have to add a few more components. You have to add the S parameters in this case, because it's an S2P file. It's measured ground signal ground results, but you'll have that on the input side to the device, which is in the middle, and then the output to the board side, both terminated on the outside. Then you have to include the inductance of the device. In this case, the inductance is actually pretty high, because there's probably just one contactor, one ground connection in there. But this would be how you would actually model the performance from the device versus the performance inside a contactor. Now I'd like to get into a few different examples. This one's a 0.5 pitch amplifier with different roll 100 contactors. The contactor on the right is basically a performance plus contactor, but it's not the contactor used in this design. You can see it's a metal contactor, and you can see the darker areas on the outside are basically coaxial-like inserts for the RF signals. And in this case, and this is not part of this design, but the square opening on the bottom part of the inside of the contactor is actually a waveguide port. Typically, for a chip that's actually got a waveguide port on the outside, or maybe even a device that's an OTA type, over-the-air type device, where it's an antenna radiating outside the chip. The data on the left-hand side, you can see that the device performance is in red, and you can see that a roll 100A and a select test contactor, which is basically minimal grounding, you can actually see that at the low frequency end, there's some increased noise, basically. And you can see in the middle of the band, this is a 24 gigahertz automotive application, but you can see in the middle of the band, the light blue line basically wiggles a lot. And that's because the ground inductance isn't sufficient to test this device. And the areas where there's higher gain is actually areas where if something's not quite right, you may actually see oscillations in this device. As you get the same contactor but have ground signal ground device configuration, you can see that the performance of the green line gets closer to the red line, but it's not quite the same. You still have some noise at the low end, and there's maybe a couple dB difference inside the passband of the amplifier. But if you put this same device in a Performance Plus contactor with very low ground inductance, you can see basically it pretty much mimics the performance of the device with maybe a couple tenths of a dB loss, which basically represents the insertion loss of the contacts in the Performance Plus housing. This is a picture of the same amplifier, but in a return loss aspect. Now, amplifiers typically don't have very good return loss, and you can see that there's a lot more difference here due to ground inductance. It affects the return loss quite a bit more. But you can see that even though the Performance Plus has a little bit less return loss, it's actually very similar in form to what you're actually testing. This slide basically is the filter performance of a SAW filter in a Performance Plus housing. Now, filters, as I mentioned before, are very sensitive to ground inductance, and typically if the ground inductance isn't good enough, you'll see a decrease in the performance in band, but you'll also see maybe possibly a shifting of the filter response because they're acoustic wave filters. In this case, the ground inductance is actually very low, so the difference between the green line, which is the filter itself, and the blue line is pretty much identical, except for maybe at the very high frequency and about 50 dB down, you see a little bit more difference in the Performance Plus socket than the filter. In a lot of cases, this performance isn't even monitored, but I'm showing it from a modeled standpoint just to show that there is some difference at higher frequencies. Now I'll spend a little time talking about the digital aspects of grounding. And this slide is actually something I've presented other stuff and shown before, but it basically shows two circuit boards. The one on the left is a connector going to 1 inch of 50 ohm line to a via that goes to a strip line 2 inches of length to another via back to the top side of the board to another connector. And both the strip line layer and the top layer are grounded. But the interesting thing about this circuit board and the circuit board on the right actually has vias tying the ground planes together. So the grounds are really close to the RF signal and they follow it all the way down into the strip line and back up to the top side. So the boards are identical in terms of length and trace width, except for they've got basically 6 grounds around the via connection to the strip line and then the via connection on the output back to the top layer. And you can see just by looking at the eye diagram that the one on the right is way better than the one on the left. And the only difference here is how the person actually laid out the circuit board. So the board actually has a big effect on signal integrity of the system. Now I want to spend a little time talking about ground inductance paths. If you look at a device in a contactor, I kind of show the internal connections, in this case wire bonds, but obviously each wire bond has an inductance, and the more you have going to the ground plane, the less ground inductance you actually have, as shown by the figure on the right. In the socket, you basically have ground inductance through the insert, which is in the middle, and then you have contacts in the insert, and the effective inductance is basically parallel path summation, as I discussed before in the back of the envelope calculation, to get an equivalent ground inductance. And then on the bottom in the C portion, you have basically a low board with vias. So all these vias actually act as extra paths to ground. The more vias you have, the lower the ground inductance from the top side of the board to the ground plane you'll have. And you can see from the right side that you have all these summations of inductance, and if one of them is really poor, you might not be able to get the results that you actually want. For instance, if you design the device so it's very close or has no margin for testing or adding extra ground inductance, then what will happen is it'll be very hard to test it in a socket. It may work fine if you solder it to the board, but very difficult for you to test it because you'll need a low inductance solution if there's no margin. And basically this system is basically a picture of what you would do that I described before, where you have the contactor, circuitry, or the equivalents, or the S parameters as a S2P file, and then the device with the inductance to the ground plane, and that's basically the summation of A, B, and C in this model. And then you have another contact to the output. So if you look at this, the little contact on the left-hand side would go to the chip. It would go through an amplifier on the chip, and then there'd be like in this case, a wire bond to another contact on the peripheral to the test setup or something, whatever's measuring the performance. Now I'll talk about how to improve the ground inductance in the package, contactor, and device. Inside the package, the more wire bonds or ground connections you have to the ground plane, the better off you'll be, and typically the more margin you'll have. If you can make these ground paths shorter, that's better from a ground inductance standpoint. A lot of times customers will use flip chip or mount the device on a circuit board to have paths to the ground pads or the ground plane to reduce the lengths. If these devices are actually on a substrate, making that substrate thinner, so the vias to the ground paddle are short, definitely decreases the ground inductance. Putting more grounds on the peripheral, especially around high frequency or clock signals, is real important. Because typically what happens is if you don't have ground around your RF signals, the ground path has to go through the contactor, through the board to the ground plane, and then back up to the ground on the board where the RF signal would be. And that ground path sometimes is a lot longer than having grounds inside the package that are basically set up to run parallel to the RF signal and provide a good grounding scheme all the way from the device to the connector. In terms of differential signals, it's real important, especially for clock signals, because clock signals tend to have a lot of noise, to have grounds around the two signals, and clock signals usually are run as a differential pair to help reduce that noise, versus signal-ended ground signal ground signals, which are typically outputs of amplifiers and stuff like that. Improving the contactor is real important because you want to have the best contactor possible because you have a certain amount of margin that the device will have, and you want to make sure that the ground inductance of the device is within that margin. So some of the better ways to improve the ground inductance of the contactors increase the size of the ground scheme. Optimally, a metal housing is the best you can do because you've got all that metal surface and ground connections and ground paths from the device ground to the low board ground. Also, this type of contactor is actually really good for thermal applications because now you've got something that can dissipate the heat. So in power amps that are definitely high frequency or high gain, you now also have a solution to get rid of the heat if you have a lot of heat, because a lot of amplifiers aren't necessarily even close to 100% efficient. So they tend to generate heat. You want to increase the number of ground connections to the ground plane, i.e. more contacts in parallel. That's kind of the picture of the insert that I showed where it had 12 contacts in the ground plane. Not only do you increase the number of ground paths, but with our contacts, they do have a wiping action, so you can make sure, especially on devices that are more like matte tin with oxides, being able to get through the oxide layer to the actual metal is real important in terms of keeping the inductance low and allowing maintenance to happen at a much bigger interval. Reducing the height of the housing to shorten the ground path is another way to improve performance. A roll 100 is basically a 1 millimeter contact. A roll 200 is basically a 2 millimeter contact. The housing heights are a little shorter than that because the contacts come in at an angle. But obviously the roll 100, because it's shorter, will have much better bandwidth than a roll 200 can handle higher frequencies. Since the RF signals route on the face of or surface of the area around the ground, around the contacts or grounding, you want to increase that surface area from the device ground to the board ground. Other things you can also do too, thicker contacts are better than thinner contacts if you have to use the same number of contacts, but a lot of times you can get a lower ground inductance by using more thinner contacts in parallel than a better thicker contact, especially if you have, let's say, 6 thinner contacts versus 4 thicker contacts. That tends to actually decrease the ground a little bit. You want to make sure the contact to device where the package ground connections are to reduce the path to the board ground plane. This is real important for really small devices where maybe they only have a couple wire bonds from the inside chip of the package to the ground paddle. You actually want to make connections to where them connections are to the ground paddle to increase or decrease the length to the ground plane of the board. So a lot of times for very small devices, this is important. For sometimes larger devices with larger ground planes, this isn't necessarily a significant thing to worry about. You want to make sure the inserts and the contacts are making good contact to the ground pad on the board. A lot of times you obviously want to put your vias as close as possible to contacts, but you don't want to put them right underneath the contacts because sometimes that impacts the mechanical performance. And if the mechanical performance is compromised, usually electrical performance is degraded also. Now, improving the grounding on a low board, some of the things you can do is you can decrease the substrate thickness to ground planes. This is something that I did in a previous life where the higher frequency we had to go, the thinner the substrate had to be in order to support the stuff that we had on the top layer. In fact, in the 80 gigahertz range, you typically have a 4 or 5 mil substrate. In the millimeter range, in the 20 to 40 gigahertz, 10 millimeters or 10 mil substrates are probably okay. Lower frequencies, you may be able to get by with a 20 mil substrate for the RF signals to the ground plane. Typically, to improve grounding on the low board, you want to add via fences. What that basically is a ground around the critical signals and then vias to the ground plane. Especially in clock signals or differential signals, you want to make sure you have that via fence so your noise from the clock signals isn't transmitted to some of the sensitive RF signals. Also, one thing I found from laying out a lot of boards, you want to basically route the highest frequency signal first, and you want to route that as the most direct path, and then work your way down as you go in lower in frequency, route the board out that way, and then the DC signals and stuff like that are last, and they can, hopefully avoid all the RF signals that are pretty much direct paths if you can make them direct paths. You want to make sure that, like I mentioned before, the vias are not under the contact interfaces. Via placements to the ground plane should be close to the contact to lower that path length to the ground planes, basically. So you want to reduce that ground path. Also, for high frequency signals, you want to route ground planes between the traces. And again, this is to make sure that they don't talk to each other. In conclusion, decreasing the ground inductance of the system makes it much easier to test the device. The more margin the device has, maybe the less you have to worry about the ground inductance of the contactor. But typically, most devices don't have a lot of margin, so it's real important to make sure that the contactor's the lowest inductance possible to give you the most ground inductance margin that you can have. Grounds closer to the RF signals provide a shorter return path. This is important, and this is the reason why, like in BGA devices that are at like 1.0 pitch, it may be hard to support a really high frequency such as 80 gigahertz because the adjacent grounds are so far away and the loop inductance is high versus something that might be 0.5 pitch where the loop inductance is a lot less. That's why you maybe can support a higher frequency signal. When you move grounds closer to the RF signals, you tend to lower the impedance. If you actually have a signal and ground far away, the impedance is fairly high, but as you move that ground signal closer to the RF signal, it tends to decrease the impedance a little bit. Obviously, if they touch, you have 0 ohms because the signal is basically shorted to ground. Ground inductance becomes more important the higher the frequency of the device and the more gain. Typically, we've found that a very high frequency, high gain device needs really, really good ground inductance. If the device is designed with no ground inductance, it becomes almost impossible to test the device accurately. And you'll see a lot of variations between the device performance, maybe soldered to board in the contactor if there's very little margin there. Slide, the conclusion. Some of the things that are most important this paper talked about is decreasing the ground inductance of the system makes it easier to test the device. The more more margin the device has for ground inductance, the easier it is to find a contactor that will actually allow the device to be tested accurately. Grounds closer to RF signals provide a shorter return path. Typically, if you have something at 1.0 pitch that can't support as high a frequency range as maybe a 0.5 pitch device, just because the loop inductance due to the extra length that the grounds are away from the RF signals is going to cause the whole system not to operate as high a frequency as maybe a device at a lower pitch. If you have grounds closer to the RF signals, they tend to lower the impedance of the RF signals. So something that grounds farther away from the RF signals will be higher impedance. And as that ground plane gets closer to the RF signal, it'll tend to drop the impedance a little bit. And that actually is how traces are tuned to 50 ohms, which is to match the test equipment that they're tested on. Ground inductance becomes more important the higher the frequency of the device and the more gain the device exhibits. As you deal with higher and higher frequency devices, the ground inductance becomes a bigger player and actually could cause, if it's not sufficient enough or low enough, it could actually cause the device to oscillate or not work in the devices. We've had lots of instances where a customer had a high gain device and maybe tried to get by with a standard contactor and then found that they had to move to Performance Plus or all metal type housing with coaxial inserts just because they needed a low enough ground inductance. If the device is designed with no ground margin, it basically becomes harder to test the device accurately. And if the margin's insufficient enough and the contactor has more ground inductance than the device can handle, typically what you'll see is maybe oscillations or very different performance to what you're actually expecting when you measure the device. The calculation of ground inductance in this paper is just an estimate. Typically overstates the real ground inductance by a small amount, but this provides a margin for different test conditions. And typically, if you want to make the ground inductance a little bit closer to what maybe the ground inductance of the whole system is, you also have to take into the fact that you may have some peripheral contacts that are also grounded. These will be farther away from the device, so the paths are longer, but they still will lower the effective ground inductance of the system. If you have any questions, you feel free to email me at jcsherry@johnstech.com, and I'd be more than happy to answer your questions. Thank you.
Once again, I would like to very much thank our sponsors who have made this event possible with their generosity and have also made it free to attend. Our premier sponsor, Cohu, our emeritus sponsor, Johnstech, our honored sponsors, ISC, iWind, and TSE, and our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec, SVTCL, R&D Altanova, UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Array, and Smiths Interconnect. Please, when you have an opportunity, thank them for sponsoring and making this event possible. And once again, we'd like to thank our premier sponsor, Cohu, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. And with that, I will thank you all for joining us today and look forward to seeing you back here tomorrow So thank you again for joining us and have a good day.
Thank you all.